Hello, and welcome to ZzScience. I'm glad you're here. Take a moment to relax, let your body settle, and let your mind slow down. If you'd like, you can share in the comments where you're listening from. For now, let's slow things down and begin. There's something about the night that makes the impossible feel a little closer. Maybe it's the stillness, or the way shadows soften the edges of things we thought we understood. You're here now, and that's enough. No need to rush. We're just going to think together for a while, quietly, about something that's been tugging at the edges of human curiosity for longer than most of us realize. Parallel universes, other worlds, places that might exist right alongside this one, separated by something we can't quite see or touch. And for a moment, it feels like the night opens a little wider. You don't have to believe in parallel universes to find them interesting. You don't have to be a physicist or a mathematician or anyone other than yourself. Lying here in the dark, wondering about the strange and beautiful possibilities that science sometimes uncovers. The universe we live in is already so vast, so filled with mysteries, that adding more universes to the picture might seem unnecessary, almost greedy. But the ideas didn't come from nowhere. They emerged from equations, from observations, from people trying to understand the rules that govern reality, and finding that those rules kept pointing towards something unexpected. Let's start somewhere simple, somewhere human. Think about a choice you made today. Maybe it was small, barely worth remembering. You turned left instead of right. You said yes instead of no. You picked up your phone or you didn't. These tiny moments pass through us constantly, and most of them dissolve into the background of our lives without leaving much of a trace. But there's a version of the parallel universe idea that suggests something strange. That every time a choice is made, every time an outcome could go more than one way, reality branches, splits, and both versions continue, each one just as real as the other, just unaware of each other's existence. It sounds like fiction, doesn't it? Like something invented to make a story more interesting. But the strange thing is, this idea, this many worlds interpretation, as it's called, came directly from trying to understand quantum mechanics, which is the branch of physics that describes how the smallest particles in the universe behave. And those particles, it turns out, don't behave the way larger objects do. They don't follow the rules we're used to. They exist in states of possibility until something forces them to become definite. And when scientists tried to explain why that happens, one of the answers they arrived at was, maybe it doesn't happen. Maybe all the possibilities are real, just separated into different branches of reality. That idea didn't come from a dreamer or a storyteller. It came from a physicist named Hugh Everett in the 1950s. And he was trying to solve a problem. Quantum mechanics works. It predicts the behavior of particles with stunning accuracy. But when you try to interpret what it means, when you try to understand the deeper picture of reality it's painting, things get strange. Particles seem to exist in multiple states at once, something called superposition. An electron can be in two places simultaneously. A photon can be both a wave and a particle until you measure it. And the act of measurement itself seems to change things, collapsing all those possibilities down into one outcome. But why? Why does measurement matter? What's so special about observation? Everett suggested that maybe nothing collapses. Maybe all the outcomes happen, but in different branches of reality. When you measure a particle and find it in one location, there's another version of you, in another branch, that measured it and found it somewhere else. Both versions are real. Both. Universes continue. They just can't interact with each other anymore. It's a clean solution in some ways. It removes the mystery of why observation seems magical, why the universe behaves differently when we're watching. But it introduces something even stranger, an endlessly branching tree of realities, splitting every moment, creating countless versions of history, countless versions of you, each one experiencing a slightly different sequence of events. And here, in the quiet, you might wonder what those other versions are doing. Are they lying in bed too, listening to something like this? Or did they make different choices, take different paths, end up somewhere else entirely? There's something both comforting and unsettling about the idea. Comforting because it means that other possibilities still exist somewhere, that the roads not taken weren't erased, but simply followed in another branch. Unsettling because it raises questions about what makes this version of you special. Why? This particular thread of experience is the one you're aware of. But let's slow down. We're getting ahead of ourselves. Before we dive deeper into the many worlds interpretation, it helps to understand where it came from, what problem it was trying to solve. And that means going back to the early 20th century, to a time when physics was being turned inside out by discoveries that made no intuitive sense but kept proving themselves true. In the late 1800s, physics seemed nearly complete. There were still some loose ends, some small anomalies that didn't quite fit the existing theories. But overall, scientists thought they understood the fundamental rules. Matter was made of atoms. Light was a wave. Energy moved in continuous flows. Everything could be predicted with enough information and careful calculation. The universe was like a vast clockwork mechanism, intricate but ultimately knowable. Then came the anomalies, small cracks in the picture. Light didn't quite behave like a wave in certain experiments. Atoms didn't emit energy in the smooth, continuous way that classical physics predicted. There was something called black-body radiation that refused to make sense. Objects heated to high temperatures emitted light in patterns that the old equations couldn't explain. In 1900, a physicist named Max Planck found a solution, but it was strange. He discovered that if you assumed energy wasn't continuous, if you assumed it came in discrete chunks, little packets he called quanta, then the math worked. The equations matched the observations. But Planck himself wasn't sure what it meant. It seemed like a mathematical trick, a way to make the numbers fit without necessarily reflecting something real about the universe. Except it was real. Other scientists began finding more evidence that energy came in quantized amounts. Albert Einstein, in 1905, used the idea to explain something called the photoelectric effect, showing that light itself came in particles, little packets of energy called photons. It was the beginning of quantum mechanics, though nobody called it that yet. And it was the beginning of a long, strange journey into a reality that refused to behave the way human intuition expected. As the decades passed, more pieces of the quantum puzzle fell into place. Scientists like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and many others developed the mathematical framework that described how particles behaved at the smallest scales. And what they found was deeply weird. Particles didn't have definite positions until you measured them. They existed in clouds of probability, spread out over space, only crystallizing into a specific location when observed. Heisenberg's uncertainty principle showed that you couldn't even know both the position and momentum of a particle at the same time. The more precisely you measured one, the less you could know about the other. This wasn't just a limitation of measurement tools. It was something fundamental about reality itself. At the quantum level, definiteness itself seemed to be something that emerged from indefiniteness, and nobody could quite explain how or why. Schrödinger, trying to illustrate the strangeness, came up with a thought experiment that became famous. A cat in a box with a quantum device that might or might not release poison. According to the math of quantum mechanics, until you opened the box and looked, the cat was in a superposition of states, both alive and dead at the same time. It was absurd, of course. Schrödinger meant it as a criticism, a way of showing that something was wrong with the interpretation. Cats aren't both alive and dead. Reality doesn't work that way. But the math kept working. The predictions kept matching experiments, and physicists were left with a choice. Either there was something wrong with the theory, or there was something wrong with our intuitions about reality. This is where Hugh Everett comes in, decades later, trying to make sense of it all. He was a graduate student at Princeton in the 1950s, working under a physicist named John Wheeler, and he was bothered by the same question that bothered everyone. Why does measurement change things? In the standard interpretation, called the Copenhagen interpretation after Bohr's location, the act of measurement collapses the wave function, forcing the particle to choose one definite state out of all the possibilities. But that seemed arbitrary. What counts as measurement? Does it require a conscious observer? Does the universe behave differently when humans are watching? Everett proposed something radical. Nothing collapses. The wave function, which describes all the possible states of a system, doesn't suddenly choose one outcome. Instead, all outcomes happen. When a quantum event has multiple possible results, the universe splits into branches, one for each outcome. Each branch is real. Each branch contains observers who see one definite result and are unaware of the other branches. It was elegant in a way. It removed the special role of measurement, the mysterious collapse. Everything followed smoothly from the mathematics of quantum mechanics without adding extra assumptions. But it also meant accepting that reality was constantly branching, that every quantum event created new universes, and that the number of parallel worlds was growing at an unimaginable rate. Most physicists at the time ignored the idea or dismissed it as too extravagant. Bohr and the Copenhagen interpretation dominated. Measurement caused collapse, and that was that. The details of how or why didn't matter as long as the predictions worked. Everett's many worlds interpretation was filed away, occasionally mentioned but rarely taken seriously. But ideas have a way of surviving. Over the years, as quantum mechanics continued to be successful, as its strangeness continued to resist intuitive explanation, some physicists started reconsidering Everett's proposal. Maybe it wasn't so extravagant after all. Maybe the real extravagance was assuming that observation had magical properties, that consciousness or measurement devices could somehow force reality to make choices. By the late 20th century, the many worlds interpretation had gained a foothold, not as the dominant view, but as a legitimate contender, one of several ways to make sense of quantum mechanics. And as it gained attention, it started influencing other areas of thought, spreading beyond physics into philosophy, into discussions about identity and probability, and what it means for something to be real. Because here's the thing, if the many worlds interpretation is correct, if every quantum possibility branches into its own reality, then the universe is far larger and stranger than we ever imagined. Not just in the sense of being spatially vast, though it is that too, but in the sense of containing multiple versions of history, multiple versions of every event, every person, every moment. And this version of parallel universes isn't the only one. The many worlds interpretation is just one way that the idea of multiple universes shows up in physics. There are others, arising from different questions, different areas of research. Some come from cosmology, from trying to understand the large-scale structure of the universe. Some come from string theory, from attempts to unify all the forces of nature into one coherent framework. Each one suggests that our universe might not be alone, that there might be other regions of space, other dimensions, other realities, existing alongside or beyond our own. Let's shift gears for a moment and think about cosmology, about the universe as a whole. When we look out at the night sky, we're seeing light that has traveled for vast distances, sometimes for billions of years. The farther we look, the further back in time we see, because light takes time to reach us. And what we've discovered is that the universe is expanding. Galaxies are moving away from each other, and the space between them is stretching. If you run that expansion backward in time, everything gets closer together. Eventually, you reach a point where all the matter and energy in the universe was compressed into an incredibly hot, dense state. That's the Big Bang, the beginning of the universe as we know it, roughly 13.8 billion years ago. It's not an explosion in space, but an expansion of space itself, and it's been continuing ever since. But here's where things get interesting. The Big Bang explains a lot, but it also raises questions. Why did the universe start expanding in the first place? Why is the universe so uniform, so similar in temperature and structure, in regions that are too far apart to have ever influenced each other? These questions led physicists to propose something called cosmic inflation, a brief period right after the Big Bang when the universe expanded at an incredible rate, much faster than the speed of light. Inflation smooths out irregularities, explains the uniformity we observe, and fits the data from various measurements. But inflation, if it's true, might not have stopped everywhere at once. In fact, some versions of the theory suggest that inflation is eternal, that it continues in some regions of space while stopping in others. Each region where inflation stops becomes a bubble universe, a pocket of space with its own laws of physics, its own constants of nature. Our universe would be just one bubble among countless others, each one separated by regions of space that are still inflating. This is called eternal inflation, or the multiverse hypothesis, and it's a very different kind of parallel universe than the many worlds interpretation. These aren't branches of quantum outcomes. They're separate regions of space, potentially infinite in extent, each one a universe unto itself. And because they're separated by eternally inflating space, they can't interact with each other. There's no way to travel from one bubble to another, no way to observe them directly. What makes this idea even stranger is that the laws of physics themselves might be different in each bubble. The constants that determine how particles interact, how strong gravity is, how fast light travels, these might not be universal. They might be local properties, set randomly in each bubble when inflation ends. Some bubbles might have physics that allows for stars and planets and life. Others might be barren, unable to support complex structures. We happen to live in a bubble where the constants are just right, not because our universe is special, but because we couldn't exist in any other kind. It's a humbling thought. The universe we observe, vast and ancient and filled with billions of galaxies, might be just one pocket in an even larger reality. And if eternal inflation is correct, there are infinitely many such pockets, each one an entire universe, most of them forever beyond our reach. Here at ZzScience, we try to sit with these ideas gently, letting them unfold without forcing them into neat boxes. The universe doesn't owe us simplicity, doesn't owe us comfort, But there's something beautiful about the way science keeps revealing layers beneath layers, possibilities beyond possibilities. Another route to parallel universes comes from string theory, which is an attempt to reconcile quantum mechanics with general relativity, Einstein's theory of gravity. General relativity describes how massive objects bend space and time, how gravity emerges from the curvature of space-time. It works beautifully at large scales, predicting the behavior of planets, stars, black holes. But when you try to apply it at quantum scales, at the level of individual particles, the math breaks down. You get infinities, nonsensical results, equations that can't be solved. String theory proposes that the fundamental building blocks of reality aren't point-like particles, but tiny, vibrating strings of energy. Different vibrations correspond to different particles. An electron is one vibration, a quark is another, a photon is yet another. It's an elegant idea, and it has the potential to unify all the forces of nature into a single framework. But string theory comes with its own strangeness. For the math to work, it requires extra dimensions beyond the 3 spatial dimensions and 1 time dimension we're familiar with. Depending on the version of the theory, there might be 10 or 11 total dimensions. The extra dimensions are thought to be curled up, compactified into shapes so small we can't perceive them. But the way they're curled up determines the properties of the particles and forces in our universe. And here's where another kind of multiverse emerges. There are many, many ways to curl up those extra dimensions. Each configuration gives rise to a different set of physical laws, a different possible universe. String theorists call this the landscape, and it's vast. Some estimates suggest there are 10 to the 500 different possible configurations, each one corresponding to a different universe with different properties. So, if string theory is correct, and if all these configurations are realized somewhere in the larger reality, then there's a multiverse of string theory universes, each one with its own version of physics. Like the bubbles from eternal inflation, these universes would be separate, unreachable. But unlike the inflation scenario, they're not necessarily separated in space. They might exist in different configurations of the extra dimensions, in a sense occupying the same space, but unable to interact. It's speculative, of course. String theory hasn't been confirmed experimentally, and it's not clear if it ever will be. The energies required to test its predictions are far beyond what we can achieve with current technology. But it remains one of the leading candidates for a theory of everything, and it keeps pointing toward the possibility that our universe isn't unique. The more you think about these ideas, the more they start to blend together. The many worlds interpretation says that quantum outcomes branch into parallel realities. Eternal inflation says that space itself fragments into separate bubble universes. String theory says that different configurations of extra dimensions create different possible universes. They're different mechanisms, different kinds of parallelism, but they all suggest the same underlying theme. Reality is bigger than what we can see. And there's a philosophical question lurking beneath all of this, something that matters even if you're not a physicist. If there are parallel universes, does it change anything? Does it matter to your life, to the choices you make, to the meaning you find in your experiences? In one sense, maybe not. If these other universes are unreachable, unobservable, then they're effectively fictional from our perspective. We can't visit them, can't communicate with them, can't prove they exist. They remain forever in the realm of theory. But in another sense, maybe it does matter, because the idea of parallel universes touches something deep in the human imagination, something about possibility and choice and the paths not taken. We live in a world of definite outcomes, where every decision closes off other options, where time moves in one direction and the past is fixed. But parallel universes offer a kind of consolation, a reminder that the other possibilities weren't erased. They're still real, just elsewhere, beyond the reach of this branch of reality. There's a melancholy to that, but also a strange kind of comfort. It means that nothing is truly lost, even if we can't access it. It means that the universe is richer, more full of life and variation than it appears. And maybe that's enough. Maybe it's enough to know that reality is larger than our experience of it, that there are layers and dimensions we can't perceive, but can infer, can imagine, can wonder about. Let's think about probability for a moment, about how we understand randomness and chance in a universe that might contain multiple versions of every outcome. In our everyday experience, probability is straightforward. You flip a coin and it lands heads or tails. There's a 50% chance of each outcome, and once the coin lands, one of those possibilities becomes real, while the other remains hypothetical. The coin didn't land tails, so that outcome exists only as a counterfactual, something that could have happened but didn't. But in the many worlds interpretation, both outcomes are real. The coin lands heads in one branch and tails in another. Both versions continue. So what does probability mean in that context? If all outcomes happen, why does it feel like there's randomness? Why do we experience one result and not the other? The answer has to do with the measure of reality, with how many branches correspond to each outcome. In quantum mechanics, the wave function assigns amplitudes to different possibilities, and the square of those amplitudes gives the probability of each outcome. In the many worlds interpretation, those amplitudes correspond to the thickness or weight of the branches. An outcome with higher probability creates more branches or thicker branches, so that more versions of you experience that result. When you flip a quantum coin, you split into two branches, one for heads and one for tails. Both are real, but the branch that aligns with the higher probability is more common, in a sense. If you could zoom out and see all the branches together, you'd see that the distribution matches the probabilities predicted by quantum mechanics. You, as an individual observer, can't experience all the branches at once. You only see one outcome. But across the multiverse of branches, the statistics work out. It's a subtle idea, and it's been the subject of much debate. Some physicists and philosophers argue that the many worlds interpretation doesn't actually solve the problem of probability, that it just shifts it to a different question. Why should you expect to find yourself in a branch with a probability that matches the wave function amplitudes? Others argue that it's the most natural explanation, that probability emerges from the structure of the multiverse without needing to invoke collapse or special rules for measurement. But, regardless of how you interpret it, the idea points towards something interesting, that probability might not be about ignorance or randomness in the usual sense. It might be about the structure of reality itself, about how many ways things can happen, and how those ways are distributed across the landscape of possible worlds. And this connects to a broader question about what it means for something to be possible. In everyday language, we talk about possibilities as things that could happen but might not. You could take a different route to work tomorrow. You could have chosen a different career. These are possibilities in the sense that they're consistent with the way the world works, with the laws of nature and the circumstances you find yourself in. But they remain hypothetical unless they actually occur. In a multiverse, though, the distinction between actual and possible blurs. If every possibility branches into its own reality, then possibility itself becomes a kind of actuality. The route you didn't take exists in another branch. The career you didn't pursue is being lived by another version of you. Possibility stops being purely abstract and becomes part of the fabric of reality. This might sound like wordplay, like a philosophical game with no real consequences, but it touches on deep questions about how we think about ourselves, about identity and continuity. If there are countless versions of you, each experiencing a different sequence of events, what makes you you? Is it your memories, your experiences, the specific thread of consciousness that connects your past to your present? Or is there something else, some essential quality that persists across the branches? There's no easy answer. Personal identity is already a puzzle in a single universe, complicated by questions about how much you can change and still remain the same person. Adding parallel universes makes it even more complex. But it also opens up new ways of thinking about the self, about what it means to be a person in a reality that might contain multiple versions of every person. Some philosophers have argued that the many worlds interpretation undermines meaning, that if every choice plays out in some branch, then no choice really matters. You might worry about making the right decision, about choosing wisely, but somewhere in the multiverse, you made the opposite choice, and both outcomes are equally real. So why bother? Why not just flip a coin and let chance decide? But that's a misunderstanding, a confusion between what happens across all branches and what happens in this branch. Yes, other versions of you are making different choices, experiencing different outcomes. But that doesn't make your choices irrelevant. You still exist in this branch, with these experiences, these consequences. The fact that another version of you exists elsewhere doesn't diminish the reality of your life, doesn't make your joys less joyful or your sorrows less painful. In fact, you could argue the opposite, that the many worlds interpretation makes choices more meaningful, not less. Because it means that every possibility is preserved, that nothing is erased. The outcomes you create with your decisions are real and lasting, contributing to the richness of the multiverse. You're not just choosing for yourself. You're choosing which branch of reality you're contributing to, which version of the story you're helping to tell. There's something almost poetic about that, something that fits with the way we intuitively feel about choices even if we don't believe in parallel universes. We sense that our decisions matter, that they shape not just our own lives but the world around us, that they ripple outward in ways we can't fully predict. The many worlds interpretation gives that intuition a kind of cosmic validation, suggesting that every choice literally creates new worlds. But let's pull back from the philosophical tangles for a moment and return to the science, to the question of whether any of this is testable. Because that's the challenge with parallel universes. If they're truly separate, if there's no way to observe them or interact with them, then how can we ever know if they're real? Science is supposed to be about evidence, about making predictions that can be tested and verified. If parallel universes are forever beyond our reach, do they belong in science at all? Or are they just speculation? It's a fair question, and scientists have been grappling with it for decades. The standard answer is that theories aren't judged solely on whether they make predictions about observable phenomena. They're also judged on how well they explain existing data, on their simplicity, on their internal consistency, on how naturally they fit with other established theories. A theory that requires fewer assumptions, that makes sense of puzzling observations without adding extra complications, is considered more elegant, more likely to be true. By that measure, some versions of the multiverse hold up well. The many worlds interpretation, for example, doesn't add anything new to quantum mechanics. It's just taking the mathematics seriously, following the equations where they lead without imposing an extra collapse mechanism. If you accept quantum mechanics, and if you want to avoid the special role of measurement, then the many worlds interpretation is almost forced upon you. It's the simplest, most straightforward reading of the theory. Eternal inflation is similar. It's not something invented to explain parallel universes. It's a natural consequence of certain models of cosmic inflation, which were developed to solve real problems in cosmology. If inflation happens, and if the fields that drive it behave in certain ways, then eternal inflation follows. The multiverse is a prediction, not an assumption. String theory's landscape is more speculative, partly because string theory itself hasn't been confirmed. But if string theory turns out to be correct, then the landscape comes along with it. You can't have one without the other. The vast number of possible configurations isn't a problem to be solved. It's a feature of the theory, a consequence of the mathematics. So while parallel universes might not be directly observable, they're not arbitrary inventions either. They emerge from theories that are trying to explain other things, theories that have their own reasons for being taken seriously. And that's often how science works. You develop a theory to explain one set of phenomena. It ends up predicting other things you weren't expecting. Sometimes those predictions can be tested, and sometimes they can't, but they're still part of the package. There have been some proposals for indirect tests, though. For example, if eternal inflation is correct, and if our bubble universe collided with another bubble at some point in the past, there might be a trace of that collision in the cosmic microwave background, the faint glow of radiation left over from the Big Bang. Cosmologists have looked for such signals, and so far they haven't found anything definitive. But the search continues, and it's possible that future observations could provide evidence one way or the other. Similarly, some versions of the many worlds interpretation suggest that quantum mechanics might behave slightly differently than expected in certain extreme situations, and those deviations might be testable. The experiments would be difficult, requiring exquisite precision and control, but not impossible. If such tests ever become feasible, we might be able to distinguish between different interpretations of quantum mechanics, including the many worlds view. But even without direct tests, the idea of parallel universes influences how scientists think about other problems. It shapes the questions they ask, the models they build, the explanations they consider. And sometimes, that's enough. Science isn't just about proving things definitively. It's about exploring possibilities, about mapping the landscape of ideas and seeing where they lead. And for those of us who aren't physicists, who are just trying to make sense of the universe from the outside, parallel universes offer something else. A reminder of how much we don't know, how much remains mysterious and open. The universe we inhabit is already strange enough, already full of phenomena that defy common sense. Adding parallel worlds to the picture just makes it stranger, richer, more full of wonder. Temptation sometimes to want answers, to want science to settle things once and for all. But that's not really how it works. Science is a process, not a destination. It's about asking better questions, refining our models, getting closer to the truth even if we never reach it completely. And parallel universes, whether they exist or not, are part of that process. They're part of the way we explore the boundaries of reality, testing our assumptions, imagining what lies beyond the edges of what we can see. So where does that leave us, here in the quiet, thinking about all these worlds that might exist beyond our own? It leaves us with questions mostly. Questions about what's real, what's possible, what it means to exist in a universe that might be just one among many. And maybe that's okay. Maybe the questions are more important than the answers, at least for now. Because the act of wondering, the act of thinking about these ideas, changes something. It shifts your perspective, makes the familiar a little strange, the impossible a little closer. You start to see the world differently, to notice the contingency of things, the way every moment could have gone differently, the way reality feels both solid and fragile at the same time. And there's something calming about that, in its own way. Not because it makes the world simpler or easier to understand, but because it makes it more full, more alive. The universe isn't a cold, mechanical system ticking along according to fixed rules. It's a wild, creative place, constantly branching, constantly exploring new possibilities, constantly surprising us with what it contains. That's the spirit we're aiming for here, in these long, quiet explorations. Not to pin things down, not to give you final answers, but to open up space for wonder, for curiosity, for the kind of thinking that doesn't have a destination in mind. Just the pleasure of following an idea wherever it leads, letting it unfold slowly, trusting that the journey itself is worthwhile. The night is long, and there's no rush. We have time to think, time to imagine, time to let these ideas settle into our minds like dust settling onto the surface of a quiet room. Parallel universes, if they exist, are in no hurry to reveal themselves. They've been there all along, waiting, just beyond the edges of what we can perceive. And whether they're real or not, the fact that we can imagine them, the fact that our equations point toward them, says something about the universe and about us. It says that reality is bigger than our senses can grasp, that there are layers and dimensions we can only infer, not experience directly. And it says that we're capable of thinking beyond our immediate experience, of constructing ideas that transcend the limits of what we can see and touch. That's a remarkable thing when you stop to consider it. A species of primates on a small planet, using mathematics and observation and careful reasoning to peer into the deepest structures of reality, to ask questions that might not have answers, at least not yet. There's a humility in that, but also a kind of pride. Humility because it reminds us how small we are, how limited our perspective. Pride because it shows what we're capable of, how far our minds can reach, even when our bodies are confined to this one world, this one thread of experience. And maybe that's the real value of thinking about parallel universes. Not whether they're true, but what they reveal about the nature of inquiry, about the human capacity to wonder and imagine and explore. We're not content with the surface of things. We want to know what lies beneath, what lies beyond, what's possible, even if it's not actual. And that drive, that restless curiosity, is part of what makes us human. So let's keep going. Let's keep thinking, keep wondering, keep following these ideas into the quiet corners of the night. There's more to explore, more layers to uncover. Parallel universes aren't just a topic in physics. They're a lens, a way of seeing the world that opens up new questions, new possibilities. And we're just getting started. Somewhere in the space between sleeping and waking, the mind does interesting things. It loosens its grip on the categories it uses during the day, the sharp distinctions between real and imaginary, possible and impossible. And maybe that's the best state for thinking about parallel universes, this soft, liminal space where ideas can float without needing to be pinned down immediately. We're going to stay in that space for a while longer, drifting through concepts and images, letting the science and the philosophy and the quiet human questions weave together. One thing that's easy to lose sight of when you're talking about parallel universes and quantum mechanics and cosmic inflation is that all of this started with people looking at the world and noticing things that didn't fit. Science isn't abstract. It's grounded in observation, in the stubborn refusal of nature to behave the way we expect. The equations and theories come later, after someone has spent years staring at data, trying to make sense of patterns that seem nonsensical. Take quantum mechanics. It didn't begin with someone sitting in a chair, thinking about the nature of reality. It began with labs, with experiments, with careful measurements of how light interacts with matter. The photoelectric effect, for instance, where light shining on metal releases electrons. Classical physics said that brighter light should release electrons with more energy. But that's not what happened. The energy of the electrons depended on the color of the light, not its brightness. Blue light released more energetic electrons than red light, no matter how bright the red light was. Einstein explained this by proposing that light comes in packets, photons, each carrying a specific amount of energy determined by its frequency. Brighter light just means more photons, not more energetic ones. It was a radical idea at the time, contradicting the wave theory of light that had been successful for decades. But it fit the data, and eventually it became the foundation of quantum mechanics. The point is, these ideas didn't come from nowhere. They came from paying attention, from being willing to follow the evidence, even when it led somewhere strange. And that's still how science works today. The parallel universes we've been talking about aren't flights of fancy. They're attempts to make sense of observations, to build theories that fit what we actually see when we look at the universe. But let's think about something else for a moment. Let's think about time. Because time is strange too, in ways that intersect with the idea of parallel universes. In our everyday experience, time flows forward. The past is fixed, unchangeable. The future is open, full of possibilities. And the present is this moving point, this now, that separates what has been from what might be. But physics doesn't really see time that way. In relativity, time is just another dimension, woven together with space into a single fabric called space-time. Events don't happen in time. They exist at specific locations in space-time, and the order in which we experience them depends on our motion, our perspective. What's past for one observer might still be future for another, if they're moving relative to each other at high speeds. This is called the relativity of simultaneity, and it's one of the most counterintuitive aspects of Einstein's theory. It means that there's no universal now, no single present moment that extends across the entire universe. Different observers, moving at different speeds, will disagree about which events are happening at the same time. And they're both right, in their own reference frames. So time isn't the simple, flowing river we imagine. It's more like a landscape, with events spread out across it, and your path through that landscape determines the order in which you encounter them. The past, present, and future all exist, in a sense, just at different locations in space-time. Moving through time, experiencing events one after another, but from a larger perspective, it's all just there, all at once. This view of time is called eternalism, or the block universe, and it has interesting implications. If the past and future are just as real as the present, if they exist in the same way, then what does that say about change, about becoming? Are we really moving through time? Or is that just an illusion, a feature of our consciousness rather than a feature of reality itself? And how does this relate to parallel universes? Well, if you combine eternalism with the many worlds interpretation, you get something even stranger. Not just a block universe, but a branching block universe, where every possible history exists as a different path through space-time. The future isn't a single destination. It's a vast tree of possibilities, all equally real, all coexisting in the larger structure of reality. You, at this moment, are at a branching point. Every decision you make, every quantum event in your vicinity, creates new branches, new futures, and all of them are real. All of them are happening, just in different parts of the multiverse. From your perspective, you're moving forward through time, experiencing one branch. But from a larger perspective, all the branches exist simultaneously, spread out across the landscape of possibilities. It's dizzying, isn't it? The more you think about it, the more your intuitions start to bend and shift. But there's also something liberating about it. If all the possibilities are real, if every choice leads to a different branch, then there's no such thing as the right choice, the one true path. There are just different paths, different versions of the story, and they're all valid, all part of the fabric of reality. That doesn't mean choices don't matter, as we talked about before. They still shape your experience, your branch of the multiverse. But it takes away some of the pressure, the anxiety of making sure you choose correctly. Because in a sense, you don't have to choose. All the options play out, just in different branches, and you get to experience one of them while other versions of you experience the others. Of course, this is all speculative. We don't know if the many worlds interpretation is correct. We don't know if the block universe is the right way to think about time. These are ideas, models, ways of making sense of the equations and observations. But they're powerful ideas, and they've shaped how physicists and philosophers think about reality. And they've seeped into the culture too, into stories and movies and conversations. The idea of parallel universes has become part of the collective imagination, a way of thinking about possibility and choice and the nature of reality. Even people who've never studied physics have some sense of what it means, some intuition that there might be other worlds out there, other versions of themselves living different lives. There's a reason for that, I think. The idea resonates with something deep in the human experience, something about the way we think about our lives, our decisions, the roads not taken. We all carry around a sense of the other possibilities, the other selves we might have been. And parallel universes give that sense a kind of reality, a framework for thinking about it not just as imagination, but as something that might actually exist. But let's shift gears again and think about scale. One of the challenges with understanding parallel universes is that they operate at scales so far removed from everyday experience that it's hard to get a grip on them. Quantum mechanics deals with particles so small that we can't see them, can't touch them, can barely even measure them without disturbing them. And the multiverse, if it exists, is so vast that even the observable universe, with its hundreds of billions of galaxies, is just a tiny fragment of the whole. So how do we make sense of these scales? How do we think about things that are so far beyond our direct experience? One way is through analogy, through finding patterns and similarities with things we do understand. But analogies have limits. They can illuminate one aspect of a concept while obscuring others. And sometimes, the things we're trying to understand are so strange that no analogy really captures them. Take the idea of quantum superposition, for example. People sometimes explain it by saying that a particle is in two places at once, like a person being in two rooms simultaneously. But that's misleading. The particle isn't literally in two places in the way a physical object would be. It's in a state of indefiniteness, a kind of limbo where its location isn't determined. And when you measure it, you don't reveal where it was all along. You force it to become definite, to take on a specific location. Or at least, that's one way to interpret it. In the many worlds interpretation, the particle is in both locations, but in different branches of reality. Your measurement doesn't force it to choose. It forces you to split into two versions, one that sees the particle in one location and another that sees it in the other location. Both versions are real, just unaware of each other. It's a subtle difference, but it matters, because it changes the picture of what's happening, of what measurement is doing, of what reality is like at the quantum level. And no simple analogy can capture all of that. You have to sit with the math, with the equations, and let them guide your intuition, even when they lead somewhere counterintuitive. But here's the thing. Counterintuitive doesn't mean wrong. Some of the most successful theories in physics are deeply counterintuitive. Relativity says that time slows down when you move fast, that clocks on satellites tick at a different rate than clocks on the ground. That's bizarre, but it's true, and GPS systems have to account for it to work properly. Quantum mechanics says that particles can be entangled, connected in ways that don't depend on distance, so that measuring one instantly affects the other, even if they're light years apart. That's strange, but it's been verified in countless experiments. The universe doesn't care about our intuitions. It operates according to its own rules, and those rules sometimes defy common sense. That's not a flaw in the universe. It's a limitation of our intuitions, which evolved to deal with medium-sized objects moving at medium speeds in a world where quantum effects and relativistic corrections are negligible. We're good at navigating that world, but we're not naturally equipped to understand the extremes, the very small, or the very fast, or the very massive. That's why we need science, why we need mathematics, why we need careful observation and rigorous thinking. These tools extend our understanding beyond the limits of intuition, letting us explore domains that we could never access through common sense alone. And parallel universes, whatever their ultimate status, are part of that exploration. They're part of the way we push against the boundaries of the known, testing our assumptions, seeing how far the theories can reach. And there's something exciting about that, even if it's also a little unsettling. Because it means that reality is still surprising us, still revealing new layers, still refusing to fit into neat, comfortable categories. We thought we understood the universe, and then quantum mechanics came along and turned everything upside down. We thought we understood space and time, and then relativity showed us that they're not what we assumed. We thought we understood the cosmos, and then we discovered dark matter and dark energy, mysterious substances that make up most of the universe but that we can't see or touch. Parallel universes are just the latest chapter in that ongoing story, the latest way that reality has surprised us. And maybe they're not the last. Maybe there are more layers still waiting to be uncovered, more strangeness lurking beneath the surface. Or maybe parallel universes are as far as the strangeness goes, the final frontier of weird. We don't know yet. We're still exploring, still asking questions, still following the evidence wherever it leads. Let's think about mathematics for a moment, because mathematics plays a strange role in all of this, one that's worth reflecting on. When physicists develop theories, they use math to describe the patterns they observe, to make predictions, to test ideas against data. And often, the math leads them to conclusions they didn't expect, predictions that seem bizarre or implausible, but that turn out to be true. Dirac's equation, for instance, which describes the behavior of electrons, predicted the existence of antimatter before anyone had observed it. The math said there should be particles with the same mass as electrons but opposite charge, and a few years later, such particles were discovered. The positron, the antiparticle of the electron, was found in cosmic rays, exactly as the equation predicted. That's a common pattern in physics. The math often knows things before the physicists do. It points toward features of reality that no one expected, that seem impossible or unnecessary, but that turn out to exist. And that raises a deep question. Why is mathematics so effective at describing the universe? Why do equations written on paper correspond so precisely to the behavior of physical systems? Some people think it's just a coincidence, a fortunate accident that the universe happens to be mathematical enough for us to describe it. Others think there's something deeper going on, that mathematics isn't just a tool we use to model reality, but is somehow built into the fabric of reality itself. The universe is mathematical, in some fundamental sense, and that's why math works so well. This is sometimes called the unreasonable effectiveness of mathematics, a phrase coined by physicist Eugene Wigner. And it's genuinely mysterious. There's no obvious reason why abstract mathematical structures should correspond to physical phenomena. But they do, again and again, with stunning accuracy. And this connects to parallel universes, because many of the arguments for their existence are mathematical. The equations of quantum mechanics, taken at face value, describe a universe that branches into multiple realities. The equations of cosmic inflation, under certain conditions, predict eternal inflation and a multiverse of bubble universes. The equations of string theory give rise to a vast landscape of possible configurations. So if you trust the math, if you believe that mathematics is telling us something deep about reality, then you almost have to take parallel universes seriously. Not as proven, not as certain, but as real possibilities, as features of the world that the equations are pointing toward. But there's a counter-argument too. Maybe the math is just a tool, and we shouldn't read too much into its predictions. Maybe some of the things that show up in equations are artifacts of our modeling choices, features of the mathematical framework rather than features of reality. Maybe parallel universes are like that, mathematical curiosities that don't correspond to anything real. It's hard to say. And different scientists and philosophers come down on different sides of the question. Some are realists, believing that if the math predicts something, we should take it seriously as a possible feature of reality. Others are instrumentalists, believing that math is just a tool for making predictions, and we shouldn't assume that everything in the equations corresponds to something real. Here at ZzScience, we don't have to settle the question. We can hold both possibilities lightly, acknowledging the power of mathematics while staying humble about its limits. The universe is under no obligation to be mathematical, even though it seems to be. And the equations are under no obligation to tell us the whole truth, even though they've been remarkably successful so far. What we can say is that the mathematical arguments for parallel universes are worth taking seriously, worth thinking about, worth exploring. They're not just wild speculation, they're grounded in well-developed theories, theories that have proven their worth in other contexts. And that's enough to justify curiosity, to justify spending time thinking about what it would mean if they're true. Let's come back to something more human for a moment. Let's think about memory, about the way we carry the past with us, the way it shapes who we are. Memory is strange when you really examine it. It's not like a recording, not like a video you can play back with perfect accuracy. It's reconstructive, constantly being edited and updated, influenced by new experiences and emotions. Every time you remember something, you're not accessing a stored file, you're rebuilding the memory. From fragments, piecing it together based on what you think happened, what makes sense given what you know now. And that process introduces errors, distortions, gaps. Your memories are real to you, but they're not necessarily accurate. They're interpretations, stories you tell yourself about the past. And if memories are unreliable in a single timeline, imagine how much more complicated they would be in a branching multiverse. Every version of you has slightly different memories, shaped by the different events they've experienced. And because the branches are separate, because there's no communication between them, Each version thinks their memories are the true history, the one real past. But they're all real, all equally valid, just different. The past isn't a single fixed sequence of events. It's a tree of possibilities, with each branch having its own version of history. And you, in this branch, carry one version of that history, one set of memories, while other versions of you carry different ones. That's a strange thought, but it also highlights something important about memory and identity. We think of ourselves as continuous beings, persisting through time, shaped by our past. But if the past is branching, if there are multiple versions of history, then what does it mean to be shaped by the past? Which past? Which version of events? Maybe the answer is that it doesn't matter. You're shaped by the past you remember, by the history that led to this branch, this moment. Other versions of you are shaped by different pasts, and that's fine. They're different people in a sense, even though they share a common origin. Identity isn't something that persists across the multiverse. It's local, specific to each branch. Or maybe identity is something else entirely, something that can't be captured by memories or experiences or any physical criterion. Maybe there's a sense in which all the versions of you are the same person, connected by something deeper than shared history. But if so, it's hard to say what that something is. Hard to pin it down in a way that makes sense. These are old philosophical questions, tangled and difficult, and adding parallel universes to the mix doesn't make them any easier. But it does give us new ways to think about them, new angles to explore. And sometimes, the value of an idea isn't that it solves a problem, but that it opens up new questions, new ways of seeing. Let's think about creativity for a moment, about the way ideas emerge, the way artists and writers and scientists come up with new things. There's a sense in which creativity involves exploring possibility space, trying out different combinations, seeing what works and what doesn't. A composer experiments with different melodies, different harmonies, searching for something that resonates. A writer tries out different plot structures, different character arcs, seeing what tells the story best. In a single universe, most of those experiments remain hypothetical. You try one version, and if it doesn't work, you discard it and try another. The rejected versions exist only in your imagination, as might-have-beens that never became real. But in a branching multiverse, every experiment is real. Every version you try exists in some branch, fully realized, playing out its consequences. The melody you almost wrote, the plot you almost chose, the scientific theory you almost developed, they're all real somewhere, in branches where you made different choices. That's a curious kind of completeness, a sense in which the creative process is more thorough, more exhaustive than it seems from inside a single branch. You might feel like you're discarding possibilities, narrowing down to the best option. But from the perspective of the multiverse, you're not discarding anything. You're just choosing which branch to continue in, while other branches continue with the other options. Does that change the nature of creativity? Does it make it less meaningful, less important? I don't think so. Because what matters, from your perspective, is the version you end up with, the choices you make in this branch. The other versions are real, but they're not yours, not in the sense of being part of your experience. They belong to other versions of you, in other branches, and that's a different story. But there's something comforting about the idea that the rejected possibilities aren't lost, that they exist somewhere, fully realized. It means that every creative impulse, every flash of inspiration, every experiment contributes to the richness of the multiverse, even if it doesn't work out in your branch. Nothing is wasted. Everything adds to the whole. That might be reading too much into it, projecting human values onto the impersonal structure of the multiverse. But then again, the universe doesn't have to care about our values for us to find meaning in it. We create meaning, we find patterns, we tell stories about the world and our prompt place in it, and parallel universes, if they exist, are part of that world, part of the larger story we're trying to understand. Let's think about another aspect of the multiverse idea, one that's less discussed but equally interesting: the question of resources. If there are infinite parallel universes, or even just a very large number of them, then there's a sense in which the resources of reality are infinite. Every particle, every bit of energy, exists not just once, but countless times, spread across the branches or the bubbles or the configurations of extra dimensions. That's a strange kind of abundance, very different from the resource constraints we're familiar with. In our everyday experience, resources are limited. There's only so much energy, so much matter, so much space and time. We have to make choices about how to use them, how to allocate them, knowing that using them one way means not using them another way. But if the multiverse is real, that scarcity is an illusion, at least from a larger perspective. The resources are effectively infinite, because every use of them in one branch is accompanied by different uses in other branches. The energy you spend here is also being spent differently elsewhere. The matter that makes up your body also makes up other versions of you, living other lives. Of course, this doesn't help you personally. You still live in one branch, with the resources available in that branch, and you still have to make choices about how to use them. The abundance of the multiverse doesn't translate into abundance within your experience. But it does shift the philosophical picture, the sense of what's possible, what's real, what exists. And it connects to questions about probability and fine-tuning that we touched on earlier. One of the puzzles in cosmology is that the constants of nature seem to be fine-tuned for life. If gravity were a little stronger or weaker, if the electromagnetic force were a little different, if the mass of the electron was slightly changed, then stars wouldn't form, or atoms wouldn't be stable, or chemistry wouldn't work the way it does. And without those features, life as we know it couldn't exist. Some people see this fine-tuning as evidence of design, as suggesting that the universe was set up specifically to allow for life. But the multiverse offers a different explanation. If there are countless universes with different constants, then some of them will inevitably have constants that allow for life. We find ourselves in one of those universes, not because it was designed for us, but because we couldn't exist in any other kind. This is called the anthropic principle, and it's been controversial. Critics argue that it's not really an explanation, that it just pushes the mystery back a step. Why is there a multiverse with all these different constants? Why not just one universe with one set of constants? And if you're willing to accept a multiverse to explain fine-tuning, why not accept design instead? But proponents argue that the multiverse isn't invented just to explain fine-tuning. It emerges from other theories, theories that were developed for independent reasons. Eternal inflation, string theory, the many worlds interpretation. These weren't cooked up to solve the fine-tuning problem. They came from trying to understand quantum mechanics, cosmology, the unification of forces. The multiverse is a consequence of those theories, and the anthropic explanation for fine-tuning is just a bonus, an additional puzzle that the multiverse happens to solve. It's a subtle argument, and it depends on how you weight different kinds of evidence, different kinds of reasoning. But it's part of the ongoing debate about what parallel universes mean, what role they play in our understanding of reality. The night deepens, and the ideas keep unfolding, layer after layer, each one revealing new questions, new connections. Parallel universes aren't just a single concept. They're a constellation of ideas, each one approaching the same basic question from a different angle. Is our universe all there is, or is it part of something larger? And that question matters, even if we can't answer it definitively. It matters because it shapes how we think about existence, about possibility, about the nature of reality itself. It matters because it pushes us to think beyond the immediate, beyond the observable, to consider what might lie beyond the edges of our experience. Science is good at that, at pushing boundaries, at asking uncomfortable questions. But it's also humble in its way. It doesn't claim to have all the answers. It offers models, theories, frameworks for thinking about the world. And those frameworks are always provisional, always subject to revision in light of new evidence. Parallel universes are part of that ongoing process. They're not the final word on reality. They're a hypothesis, a possibility, a way of making sense of certain observations and equations. Maybe they'll be confirmed someday, through some observation or experiment we can't yet imagine. Maybe they'll be ruled out, replaced by a better theory that explains the same phenomena without invoking multiple worlds. Or maybe they'll remain forever in the realm of the theoretical, impossible to prove or disprove, a permanent fixture of the landscape of ideas. But whatever their ultimate status, they've already changed how we think about the universe. They've opened up new ways of imagining reality, new ways of understanding quantum mechanics and cosmology and the nature of existence. And that's valuable in itself, regardless of whether they turn out to be true. Because science isn't just about getting the right answers. It's about exploring the space of possible answers, mapping out the terrain, seeing what's consistent with what we know and what might lie beyond. And parallel universes, in all their strange and varied forms, are part of that exploration. They're part of the way we reach beyond ourselves, beyond our immediate experience, to grasp at something larger. And maybe that's enough. Maybe it's enough to know that the ideas exist, that they're worth thinking about, that they've emerged from serious attempts to understand the universe. We don't need them to be proven to find them interesting, to find them meaningful. We just need them to be possible, to be consistent with what we know, to open up new ways of thinking. That's the spirit of inquiry, the spirit of curiosity, the spirit that drives science forward. And it's the same spirit that brings us here, to this quiet space, thinking about parallel universes and possibility and the nature of reality. We're not trying to settle anything, not trying to reach a final conclusion. We're just exploring, wondering, following the ideas wherever they lead. And the ideas keep leading deeper, into stranger territory, into questions that don't have easy answers. But that's okay. That's part of the journey. The universe doesn't owe us simplicity, doesn't owe us comfort. It is what it is, and our job is to understand it as best we can, to build models and theories that capture its behavior, to push against the boundaries of the known. Parallel universes are part of that push. They're part of the way we test our assumptions, challenge our intuitions, explore the edges of possibility. And whether they're real or not, whether they exist or not, they've already enriched our understanding, already opened up new ways of thinking about existence and reality and the nature of the cosmos. So, let's keep going, keep thinking, keep wondering. There's still more to explore, more layers to uncover, more questions to ask. The night is long, and we're in no hurry. We're just here, thinking together, letting the ideas unfold at their own pace, trusting that the journey itself is worthwhile. The quietest hours stretch out, and the mind settles into a different rhythm. There's a kind of peace that comes from thinking about things that are too large to fully grasp, too strange to fit into familiar categories. Parallel universes, in all their varieties, offer that kind of peace. Not because they're comforting, exactly, but because they remind us that reality is bigger than our understanding, that there's always more to discover, more to wonder about. We've talked about the scientific theories, the different kinds of multiverse that emerge from quantum mechanics and cosmology and string theory. We've talked about the philosophical implications, the questions about identity and choice and meaning. But there's another dimension to all of this, something more personal, more emotional. The way these ideas affect how we see ourselves, how we relate to the world around us. Because ideas aren't just abstract constructs. They shape our experience, color our perceptions, influence the stories we tell about our lives. And the idea of parallel universes, whether it's true or not, has a particular kind of emotional resonance. It speaks to something deep in the human experience, something about possibility and loss and the paths not taken. Think about the moments in your life when things could have gone differently. The decision you almost made, the opportunity you almost took, the person you almost became. We all carry these almosts with us, these shadows of other lives that we can imagine but never lived. And there's often a bittersweet quality to them, a sense of longing for something that might have been. The many worlds interpretation gives those almosts a kind of reality. It says that somewhere, in some branch of the multiverse, you did make that other decision. You did take that opportunity. You did become that other person. The life you almost lived is being lived, just not by this version of you. It's real, just elsewhere, beyond the reach of this branch. Does that make the longing easier or harder? It's hard to say. On one hand, there's a comfort in knowing that the other possibilities weren't erased, that they exist somewhere, fully realized. Nothing is truly lost. Every path is taken, just in different branches. On the other hand, it highlights the separateness, the fact that you can never access those other lives, never experience what might have been. They're real but unreachable, and that might make the sense of loss even sharper. But maybe it's not about making the longing easier or harder. Maybe it's just about seeing it differently, understanding it in a new way. The almosts are real in a sense, but they're not yours. They belong to other versions of you, and that's a different story, a different thread of experience. Your life is this branch, these choices, these consequences. And that's enough. It has to be. There's a kind of acceptance in that, a recognition that you can only live one life, only follow one thread, even if other threads exist elsewhere. And maybe that's liberating in its way. It takes away the pressure of trying to live all the possible lives, of trying to be all the possible versions of yourself. You can just be this version, in this branch, and trust that the other possibilities are being explored elsewhere by other versions in other branches. Of course, this assumes that the many worlds interpretation is correct, which is far from certain. But even as a metaphor, even as a way of thinking about possibility and choice, it has power. It offers a framework for understanding the relationship between what is and what might have been. A way of holding both the reality of your life and the reality of other possibilities without them cancelling each other out. And it connects to something broader, something about how we navigate uncertainty, how we make decisions in a world where we can't know all the outcomes in advance. Every choice is a branching point, a moment where multiple futures are possible. And we have to choose without knowing which future will unfold, which branch we'll end up in. In one sense, that's terrifying. How do you make good choices when you can't see the consequences? How do you know which path to take when all of them are shrouded in uncertainty? But in another sense, it's freeing. Because if you can't know the outcomes in advance, if the future is genuinely open, then there's no such thing as the right choice, the one true path. There are just different choices, different paths, each leading somewhere. And the many worlds interpretation takes that a step further, saying that all the paths are taken, all the choices are made, just in different branches. So in a sense, you don't have to choose, you just have to pick which branch you want to continue in, which version of the story you want to experience. The other branches will continue without you, exploring the other options, and that's okay. But again, this is all hypothetical, a way of thinking rather than a proven fact. The many worlds interpretation is one of several ways to make sense of quantum mechanics, and it's not clear which one is correct. Maybe reality does collapse, maybe measurement does have a special role. Maybe there's something we're missing that will make sense of it all in a way we haven't thought of yet. But the value of the idea doesn't depend on its truth. It depends on what it reveals, what it helps us see, what questions it opens up. And in that sense, the many worlds interpretation has already proven its worth, already contributed something valuable to the way we think about reality. Let's think about another emotional dimension of parallel universes, the sense of connection, or the lack of it. In a single universe, everyone you know shares the same history, the same sequence of events. You're all part of the same story, shaped by the same past. There's a unity to that, a sense of shared reality that binds people together. But in a branching multiverse, that unity starts to fracture. Every person is constantly splitting into different versions, following different branches. The version of someone you know in this branch might be very different from the version in another branch. They share a common origin, but their paths have diverged, shaped by different experiences, different choices. And there's a loneliness to that, a sense of isolation. Because even if you're surrounded by people, even if you have deep connections, those connections are specific to this branch. In other branches, the relationships might be different, might not exist at all. The person you love in this branch is one version among many, and you'll never meet the others, never know how those other relationships would have unfolded. But maybe there's also a richness to it, a sense of the multiplicity of connection. Every relationship contains multiple possibilities, multiple versions, each one real in its own branch. The friend you made in this timeline is just one version of that friendship, and there are others, playing out differently elsewhere. It doesn't diminish the relationship you have. If anything, it highlights its uniqueness, its specificity, the fact that this particular version is the one you're experiencing. And maybe that's the key: specificity. In a multiverse of infinite possibilities, what matters is the specific branch you're in, the specific experiences you're having, the specific people you're connected to. The fact that other versions exist doesn't make this version less real, less meaningful. It just makes it one among many, which is a different kind of truth. But these are emotional responses, personal reflections, not scientific arguments. The science of parallel universes is about equations and observations, about making predictions and testing theories. The emotions are what we bring to it, the way we integrate these ideas into our lives, our understanding of ourselves. And that's okay. Science doesn't exist in a vacuum. It's part of human culture, part of the way we make sense of the world. And when scientific ideas touch on questions of existence and meaning and identity, they inevitably trigger emotional responses, philosophical reflections, personal struggles to understand what it all means. Parallel universes are a perfect example of that. They're a scientific hypothesis with deep philosophical and emotional dimensions. And we can engage with all of those dimensions at once, holding the science and the philosophy and the emotion together, letting them inform each other without trying to reduce one to the other. Let's think about another angle, the question of probability and expectation. If there are parallel universes, if every possible outcome happens in some branch, what does that mean for how we think about the future, about what's likely to happen? In a single universe, probability is straightforward. Some outcomes are more likely than others, and over time, the likely outcomes happen more often. If you flip a coin many times, you expect it to land heads about half the time and tails about half the time. That's what probability predicts, and that's what we observe. But in a many worlds interpretation, every coin flip creates two branches, one for heads and one for tails. Both outcomes happen, so in what sense is one more probable than the other? If you split into two versions, one that sees heads and one that sees tails, then from the perspective of the multiverse, there's no randomness, no probability. Everything happens. The answer, as we discussed earlier, has to do with the measure of reality, with the thickness or weight of the branches. Outcomes with higher probability correspond to thicker branches, so more versions of you experience them. When you flip a coin, you split into two versions, but the measure is equal for both, so you're equally likely to find yourself in either branch. But this raises a subtle question. Why should you expect to find yourself in a branch whose measure matches the quantum probabilities? The many worlds interpretation says all branches are real, but it doesn't explain why your experience should follow their probabilities predicted by quantum mechanics. That's been a subject of ongoing debate, with various proposals for how to derive the Born rule, the rule that connects quantum amplitudes to probabilities, from the structure of the many worlds interpretation. Some physicists argue that the Born rule is a consequence of decision theory, of how rational agents should bet on outcomes in a branching universe. Others argue that it's built into the definition of probability itself, that probability in a branching universe just is the measure of branches. Still others think the problem hasn't been fully solved, that there's something missing in our understanding of how probability works in a many worlds context. It's a technical issue, one that matters more to philosophers and physicists than to most people. But it highlights something important, that even the most elegant theories have subtle difficulties, areas where the details aren't fully worked out. The many worlds interpretation is clean and simple in many ways, but it's not without its challenges, its open questions, and that's true of all the multiverse ideas. Eternal inflation explains a lot, but it also raises questions about how to define probabilities in an infinite multiverse, about how to make predictions when everything happens somewhere. String theory offers a framework for unifying the forces, but the landscape of possible configurations is so vast that it's hard to extract specific predictions, hard to say why our universe has the properties it does rather than some other set. These aren't fatal flaws. They're the growing pains of theories that are still being developed, still being refined. Science progresses through a process of proposal and critique, of putting forward ideas and testing them against observation and logic. And the multiverse ideas are in the thick of that process, being debated and developed by physicists and philosophers around the world. It's worth remembering that when you're thinking about these ideas, they're not finished products, not settled truths. They're works in progress, hypotheses that are still being explored. And that's part of what makes them exciting. They're at the frontier of knowledge, in the space where we're still figuring things out, still asking questions, still unsure of the answers. Let's think about something else, the role of imagination in science. Because parallel universes require a lot of imagination. You can't see them, can't touch them, can't visit them. You have to imagine what they might be like, how they might work, what it would mean for them to exist. And that imaginative work is part of the scientific process, part of how we explore possibilities, generate hypotheses, think through the implications of our theories. Einstein was famous for his thought experiments, for imagining scenarios that couldn't be physically realized, but that helped clarify the concepts. What would it be like to ride alongside a beam of light? What would, you see? That question led him to special relativity, to the realization that time and space are relative, not absolute. It was an act of imagination, but it was grounded in physics, in thinking carefully about what the laws of nature implied. Parallel universes are similar. They're not just wild speculation. They're grounded in equations, in observations, in careful reasoning. But they also require imagination, the ability to think beyond the immediate, to consider possibilities that seem strange or unlikely, to follow the logic wherever it leads. And that's a skill, a kind of intellectual flexibility that's valuable not just in science, but in life. The ability to imagine other possibilities, other ways things could be, other perspectives on a situation. It's what lets us empathize with others, understand their point of view. It's what lets us plan for the future, envision different scenarios, prepare for uncertainty. It's what lets us create, whether we're artists or scientists or just people trying to navigate a complex world. Parallel universes, in that sense, are an exercise in imagination, a way of stretching our minds, pushing against the limits of what we think is possible. And that's valuable, even if they don't exist, even if the theories that predict them turn out to be wrong. Because the act of imagining them, of thinking through their implications, expands our sense of what's possible, what's conceivable, what might be true about the universe. And it's not just scientists who engage in that kind of imagination. It's storytellers, philosophers, artists, anyone who thinks about the nature of reality and possibility. Science fiction has been exploring parallel universes for decades, long before physicists started taking the idea seriously. Stories about alternate timelines, about sliding between worlds, about versions of characters living different lives in different realities. Those stories aren't just entertainment. They're part of the cultural conversation about what reality is, what it could be, how we navigate the space of possibilities. And they feed back into science, influencing how scientists think about these questions, providing metaphors and frameworks that make the abstract concepts more concrete. There's a back and forth between science and culture, a dialogue where ideas flow in both directions. Scientists develop theories based on observations and mathematics, and those theories seep into the culture, influencing stories and art and the way people think about the world. And then the culture feeds back, offering new ways of imagining the ideas, new angles to explore, new questions to ask. Parallel universes are a perfect example of that dialogue. The many worlds interpretation came from physics, from trying to make sense of quantum mechanics. But it's been taken up by science fiction, by philosophy, by popular culture. And in the process, it's been transformed, expanded, explored in ways that go beyond the original scientific idea. And those explorations, in turn, influence how scientists think about the concept, what questions they ask, what implications they consider. It's a rich, ongoing conversation, and we're all part of it, whether we're scientists or not. Because these ideas matter, not just as technical details, but as part of how we understand ourselves, our place in the universe, the nature of reality. And that brings us back to the personal, to the emotional, to the way these ideas affect how we see the world. Because when you think about parallel universes, when you really sit with the idea, it changes something. It shifts your perspective, makes the familiar strange, the solid a little less certain. You start to see the world as contingent, as full of possibilities that could have been but weren't, or that are, but in other branches. You start to notice the branching points, the moments where things could have gone differently. And you start to wonder about the other versions, the other lives, the other realities that might exist alongside this one. That can be disorienting, unsettling. But it can also be liberating in a way, because it reminds you that this reality, this life, this moment, is just one possibility among many. It's not the only way things could be. It's just the way they are, in this branch, at this point in time. And maybe that makes it more precious, more worth paying attention to. Because if there are infinite other branches, infinite other versions, then this one is unique. This specific sequence of events, this particular arrangement of matter and energy, this exact thread of experience, it's never been before and will never be again. It's one branch among countless others, and that makes it special. Or maybe it makes it less special, less significant, just one drop in an infinite ocean of possibilities. It's hard to say. The emotional response to parallel universes is complicated, personal, dependent on your temperament and your worldview. But whatever your response, the ideas are worth thinking about, worth sitting with, worth letting unfold in their own time. Because they touch on something fundamental, something about the nature of existence and possibility, and the relationship between what is and what might be. And in these quiet hours, as the night deepens and the world grows still, there's space for that kind of thinking. Space to let the ideas breathe, to follow them wherever they lead, to see what they reveal about the universe and about ourselves. We've covered a lot of ground, wandered through quantum mechanics and cosmology and string theory, through philosophy and emotion and the role of imagination. And through it all, the idea of parallel universes has been there, threading through the different topics, connecting them in unexpected ways. It's a powerful idea, one that has captured the imagination of scientists and storytellers and ordinary people wondering about the nature of reality. And, whether it's true or not, whether parallel universes actually exist or remain forever in the realm of theory, it's already changed how we think about the universe, about possibility, about ourselves. Because that's what ideas do. They change us, shape us, open up new ways of seeing. And the best ideas are the ones that keep unfolding, that reveal new layers the more you think about them, that connect to other ideas in surprising ways. Parallel universes are like that. They're not just a single concept, but a constellation of ideas, each one illuminating different aspects of reality, different questions about existence and possibility and the nature of the cosmos. And they invite us to think deeply, to question our assumptions, to imagine what might lie beyond the edges of what we can see. That's the heart of ZzZscience, the spirit we're trying to cultivate in these long, quiet explorations. Not just learning facts, not just absorbing information, but engaging with ideas, wrestling with questions, letting the wonder and strangeness of the universe sink in. Because the universe is wonderful and strange, far beyond what our intuitions prepare us for. It contains quantum superpositions and relativistic time dilation, black holes and dark energy, the Big Bang and the possibility of parallel worlds. It's a place where the rules keep surprising us, where the deeper we look, the more we find that defies common sense. And that's okay. That's part of the adventure, part of the joy of exploration. We don't need the universe to be simple or comfortable or easy to understand. We just need to be curious, to be willing to follow the evidence and the logic wherever they lead, to be open to being surprised. Parallel universes are one of those surprises. One of the ways the universe has turned out to be stranger than we expected. They emerged from our best theories, from careful observation and rigorous reasoning. And whether they're real or not, they've enriched our understanding, opened up new questions, expanded the space of what we think is possible. So let's sit with that for a moment, here in the quiet, letting it settle. The universe might contain parallel worlds, infinite branches of reality, each one as real as this one, just separated by the structure of space-time, or the configurations of extra dimensions, or the branching of quantum outcomes. It's a vast, dizzying possibility, one that challenges our sense of what's real, what exists, what it means to be a person in a universe that might contain countless versions of every person. And yet, here we are, in this branch, this moment, this specific thread of experience. The other branches, if they exist, are beyond our reach. We can't see them, can't touch them, can't interact with them. They're as distant as anything could be, separated not by space but by something deeper, some fundamental barrier that keeps the branches apart. But we can imagine them. We can think about them, wonder about them, explore them in our minds. And that's a kind of connection, a way of reaching beyond the boundaries of this branch, even if we can't cross those boundaries physically. It's late now, or early, depending on how you measure it. The night has stretched out, long and deep, filled with ideas and questions and quiet reflections. And we're coming to the end of this particular exploration, this journey through the concept of parallel universes and all the layers and dimensions that come with it. But the ideas don't end here. They continue, evolving, branching out in new directions, connecting to other concepts, other questions. That's the nature of scientific ideas, of philosophical ideas, of any ideas worth having. They're not finished products. They're living things, growing and changing as we think about them, as we test them against new evidence, as we see what they imply and where they lead. Parallel universes are part of that ongoing conversation, part of the way we try to understand the universe and our place in it. They're a hypothesis, a possibility, a framework for thinking about reality. And they've already proven their value, not by being definitively confirmed, but by opening up new ways of thinking, new questions to explore, new connections to make. So as we wind down, as the night gives way to whatever comes next, let's carry these ideas with us. Not as settled truths, not as facts to memorize, but as invitations to wonder, to question, to imagine. The universe is vast and strange, and we're just beginning to explore it, to understand its depths and possibilities. Parallel universes remind us of that vastness, of how much we don't know, how much remains to be discovered. They remind us that reality is richer than it appears, that there are layers and dimensions we can barely perceive, that the edges of the known are just the beginning of what's possible. And in that sense, they're not just a scientific concept. They're a way of seeing the world, a lens through which everything looks a little different, a little more full of possibility. They invite us to think bigger, to question deeper, to imagine more freely. That's the gift of science, the gift of ideas like parallel universes. They expand our sense of what's possible, what's real, what might be true about the universe. And in doing so, they expand us, make us more curious, more open, more alive to the wonder of existence. So rest now, if you need to. Let the ideas settle. Let them drift through your mind as you drift towards sleep. The parallel universes, if they exist, will still be there when you wake, still branching, still exploring every possibility, still creating new worlds with every moment. And you'll still be here, in this branch, this specific thread of reality, living your life, making your choices, contributing to the richness of this particular version of the universe. That's enough. It has to be. Because it's all we have, all we can experience, all we can know directly. But knowing that other possibilities exist, that other branches are playing out their own stories, adds something. A depth, a richness, a sense of the vastness of reality. And that's worth carrying with you, worth thinking about, worth letting shape how you see the world. The night is quiet now, settling into its deepest hours. The ideas have unfolded, layer by layer, revealing the strange and beautiful possibilities that emerge from our best attempts to understand the universe. Parallel universes, in all their varieties, are part of that understanding, part of the way we map the territory of reality. They're not the end of the story, they're just one chapter, one piece of a much larger puzzle. But they're an important piece, one that connects to so many other questions about existence and possibility and the nature of the cosmos. And as we close this exploration, as we let the ideas rest, there's a sense of completion, but also of continuation. Because the questions don't end. They keep branching, keep multiplying, keep leading deeper into the mysteries of reality. And that's okay. That's the nature of inquiry, the nature of curiosity, the nature of what it means to be human in a universe that never stops surprising us. So, sleep well, if sleep finds you. And if it doesn't, that's okay too. Let the ideas drift, let them settle into whatever patterns they form in your mind. The universe, with all its parallel branches and quantum possibilities and cosmic vastness, will still be there, still unfolding, still revealing new layers with each passing moment. And you'll still be here, wondering, questioning, exploring the edges of the known. That's what we do, what we've always done, what makes us human. We look at the universe and we ask, what else is there? What lies beyond? What might be possible? And sometimes the universe answers. Not always in the way we expect, not always clearly or definitively, but it answers. Through equations and observations, through careful reasoning and bold imagination, we piece together a picture of reality that's far stranger and more wonderful than common sense suggests. Parallel universes are part of that picture, part of the ongoing revelation of what the universe is and what it contains. They're a reminder that reality is larger than our experience, that there are dimensions and possibilities we can barely grasp, that the cosmos is full of surprises waiting to be discovered. And that's enough to rest on, to let the night carry you wherever it carries you. The ideas are there, planted like seeds, ready to grow and branch and connect to other ideas in ways you can't predict. That's how understanding develops, how knowledge grows, how we slowly, incrementally, build a picture of reality that's more complete, more accurate, more full of wonder. Parallel universes, quantum branching, bubble cosmoses, string theory landscapes, many worlds. They're all different ways of saying the same basic thing. Reality is bigger than it seems. The universe we observe is just one part of something larger, something we're still trying to understand. And in the quiet of the night, in the space between waking and sleeping, that's a comforting thought. Not because it makes the world simpler or easier to navigate, but because it reminds us that there's always more to discover, more to wonder about, more to explore. The universe is vast and strange and full of possibilities. And we're here, in this branch, this moment, this specific point in the unfolding of reality, trying to understand it all. That's a remarkable thing when you stop to think about it. A remarkable privilege, a remarkable challenge, a remarkable gift. So let the ideas rest now. Let them settle into your mind, becoming part of the way you see the the way you think about reality. Parallel universes, whether they're real or not, have already changed something, opened something up, revealed something about the nature of existence and possibility. And that's the power of science, the power of ideas, the power of thinking deeply about the universe and our place in it. It changes us, shapes us, makes us more aware of the vastness and strangeness and wonder of reality. Rest now. The night is deep, and the ideas have unfolded as far as they can for now. But they'll be there when you need them, ready to be revisited, re-examined, connected to new thoughts and new questions. The universe, with all its parallel branches and quantum mysteries and cosmic possibilities, continues. And so do we, wondering, questioning, exploring. That's the human story, the story of a species that looks at the universe and asks, what else? What more? What might be possible? And the universe, in its own way, keeps answering. Through science and observation, through mathematics and imagination, through the slow, patient work of countless people trying to understand reality. The answers are strange and wonderful, challenging and inspiring, humbling and elevating all at once. Parallel universes are part of that answer, part of the picture we're building, piece by piece, of what reality is and what it contains. And whether they're ultimately confirmed or refuted or remain forever in the realm of theory, they've already enriched our understanding, already opened up new ways of thinking about existence. That's enough. That's more than enough. It's a gift, this ability to wonder and question and imagine. And it's a gift we can carry with us, into sleep or into waking, into whatever comes next. The night is quiet, the ideas rest, and somewhere, in some branch of reality, or in the vast landscape of possibility, other versions of this conversation are happening. Other versions of these ideas are unfolding. Other versions of you are wondering about the nature of parallel universes and what they mean. But here, in this branch, this moment, this specific thread of experience, it's time to rest. To let the wonder settle, to let the questions drift, to trust that the universe, in all its vastness and strangeness, will still be there, still waiting to be explored, still full of surprises. Sleep well, wonder well, and when you wake, the universe will still be there, vast and strange and full of possibilities, ready to reveal another layer, another mystery, another reason to keep wondering. Good night.